Size begins where intuition stops helping. The largest frame used in science is the observable universe, meaning the region from which light has had time to reach Earth since the beginning of cosmic expansion. This is not a claim about an edge or a boundary in space. It is a practical limit set by time and by the constant speed of light in a vacuum. When the light from a distant region arrives, it brings information that has been travelling for a very long time. Distance and time become linked because far away also means long ago. In this widest region, size is understood through three connected measures: how large structures are, how far apart they are, and how long they take to form and change. The numbers involved are not meant to be memorized here. They are meant to set proportions. A galaxy is huge compared with a star system, yet tiny compared with the span between galaxy clusters. A cluster is immense compared with a single galaxy, yet small compared with the largest voids. The mind often tries to compress these layers into one picture, but the picture becomes unstable. A calmer approach is to hold the baseline first without moving inward too quickly. The observable universe contains all directions, and on large scales it looks similar in every direction when averaged over vast distances. This is not because it is uniform in detail, but because over sufficiently large scales the distribution of matter approaches a statistical smoothness. Within that smoothness, matter is arranged in patterns created by gravity. Gravity is the long-range force that shapes the largest structures. It acts between all masses and energies, and over long time it pulls matter into denser regions. In the earliest observable epochs, the universe is hot and nearly uniform with tiny differences in density. Those small differences matter because gravity amplifies them. Where density is slightly higher, matter is drawn in making the region denser still. Where density is slightly lower, matter drains away relative to the average. Over billions of years, this produces the large-scale structure seen today. Yet even today, most of the volume of the observable universe is close to empty by everyday standards. Space is filled with extremely thin gas and faint radiation, but the density of particles in the spaces between galaxies is so low that collisions are rare. The emptiness is not an absence of reality. It is a different regime where the distance between particles can be so large that ordinary ideas about air and pressure no longer apply. In this regime, light travels with little obstruction for immense spans. The sky looks dark, not because there is nothing, but because stars and galaxies are far apart and because light takes time to travel. The baseline also includes a faint background glow called the cosmic microwave background. It is radiation left over from an early epoch when the universe cooled enough for atoms to form and for light to travel freely. Over time, as space expanded, the wavelengths of that radiation stretched, lowering its energy and shifting it into the microwave range. Today, it arrives from all directions with remarkable uniformity, with small variations that record early density differences. Those variations are a map of the seeds of structure. They show that the early universe is not perfectly smooth, and they provide a reference against which later structure can be understood. At this larger scale, the universe is also described as expanding. Expansion means that the distances between far galaxies increase over time because the fabric of space changes. This is not a local pushing force. Nearby galaxies can move toward each other under gravity. But at sufficiently large separations, the overall trend is that the separation grows. This expansion is observed through redshift, a stretching of light to longer wavelengths. The key point for intuition is that the larger scale is not a static stage. It evolves. Distance itself depends on when it is measured and on how expansion is described. Scientists use careful definitions for distance in cosmology because different questions require different measures. One measure corresponds to how far away a galaxy was when it emitted the light we now see. Another corresponds to its current separation. Another corresponds to how brightness diminishes with distance in an expanding universe. These distinctions can be technical, but the calm meaning is simple. The universe has a history, and measuring it requires language that respects that history. The observable universe is also not made only of the matter that shines. Ordinary matter made of atoms is only part of the total matter and energy inferred from observations. Dark matter is a form of matter inferred from its gravitational effect shaping the motions of galaxies and the growth of large-scale structure. Dark energy is a term for the cause of the observed accelerated expansion. What is known is that multiple independent observations, including galaxy rotation, gravitational lensing, the cosmic microwave background, and the distribution of galaxies, point to a universe where the gravitational influence exceeds what visible matter alone can provide, and where expansion accelerates over time. What remains uncertain is the fundamental nature of dark matter and the physical explanation of dark energy. These are not gaps without shape. They are defined problems constrained by data. The large-scale baseline therefore contains both high-confidence features and bounded uncertainties. It is a measured picture, not a complete one, and its incompleteness is part of its honesty. Intuition often expects that bigger means simpler, but at the larger scale, simplicity appears only after careful averaging. Individual regions are complex. Galaxies form, merge and evolve. Gas heats and cools. Black holes grow and influence their surroundings. But when seen across the whole observable volume, a coherent pattern emerges, an expanding space, filled with a web-like distribution of matter. This pattern is not directly seen in one snapshot. It is inferred from many surveys and measurements. Astronomers map galaxies across the sky and measure their redshifts, building three-dimensional catalogues. They measure faint distortions of distant galaxy shapes caused by gravitational lensing mapping mass that does not shine. They measure the cosmic microwave background, revealing early conditions. Together, these measurements define the outermost region of size. The baseline can be held as a calm statement. The observable universe is a vast evolving volume where emptiness dominates by space, gravity dominates by structure, and light dominates by information. A useful mental anchor is the idea that every distant photon has travelled through near vacuum for a long time to reach a detector. That photon carries a record of the conditions where it started and of the changes imposed by its journey. It is the messenger that links the outermost scale to local instruments. Without light, the larger scale would remain unmeasured. With light, size becomes something that can be quantified even when it overwhelms common sense. In this region, the goal is not to force intuition to match the scale instantly. The goal is to let intuition step back, allowing measurement to set the frame. The universe is vast enough that its largest features cannot be grasped by direct imagination, but they can be described by stable relationships, the finite speed of light, the expansion of space, the growth of structure under gravity, and the distribution of matter in a mostly empty volume. This completes the widest baseline of size, held steady before any inward step is taken. The wider scale becomes measurable because light carries distance as time. Light travels at a fixed speed in a vacuum, and this turns the universe into a place where looking outward is also looking backward. The idea can feel unnatural at first because daily experience treats sight as immediate. Yet even on Earth there is a delay. Sunlight takes a little over 8 minutes to reach Earth. That delay is small enough to ignore in ordinary life, but it is the same principle used at cosmic distances. For distant galaxies, the delay becomes millions or billions of years. The light arriving at a telescope is a record from the past. In this region, the aim is to stay with light travel and the way it changes what distance means before introducing other measuring tools. When a telescope collects light, it collects photons that left their sources at different times. Nearby stars in the Milky Way are seen as they were years ago. Nearby galaxies are seen as they were millions of years ago. Very distant galaxies are seen as they were when the universe was much younger. This is not a poetic statement. It is a direct consequence of finite signal speed. It means that the sky is a layered time map. Different directions and different distances reveal different epochs, and astronomy becomes a way to study cosmic history without leaving Earth. This shifts intuition. In everyday life, the past is remembered through records and artifacts. In astronomy, the past is observed directly through light. Yet the observation is still limited. Only signals that have had time to arrive can be seen. That is why the observable universe is defined the way it is. Beyond the horizon, light has not had enough time to reach Earth, so those regions are not directly observable. Light travel time is often expressed as distance using a unit called the light year, which is the distance light travels in 1 year. This unit is useful because it keeps the time link visible. Saying an object is a certain number of light years away also implies that its light is that many years old when it arrives. However, on the larger scales, this simple interpretation must be used with care, because space itself expands while light travels. Even so, light years remain a helpful way to build intuition step by step. The next piece is how light encodes information. Light has wavelength and frequency. Wavelength is the spacing between wave peaks, and frequency is how many peaks pass per second. Different wavelengths correspond to different colors in visible light, and to different types of radiation beyond visible light, such as infrared and ultraviolet. Many cosmic objects emit light across a wide range of wavelengths. Hot stars emit more visible and ultraviolet light. Cooler dust emits infrared light. Extremely energetic processes can emit X-rays and gamma rays. By observing multiple wavelengths, astronomers can infer temperatures, compositions, and physical processes. Yet even when focusing only on distance, wavelength matters because it can shift during travel. This shift is a key signal. Before reaching that, there is a more basic fact: the brightness of light falls with distance. In a simple space, light from a source spreads out in all directions, and the amount received per unit area decreases as the surface area of an expanding sphere. This is why distant objects appear dimmer. If the intrinsic brightness of the source is known, the observed brightness can be used to estimate distance. But intrinsic brightness is rarely known directly, so astronomy uses objects with predictable brightness patterns, such as certain variable stars and certain supernovae. These are tools, but this region stays with light travel time itself because it is the first constraint. If a signal is old, it must have come from far away, and it carries information about a past state of the source. That past state can be very different from the source's present state if the source has changed. A star evolves over millions to billions of years. A galaxy evolves over billions of years. A supernova changes over days and weeks. When observing distant supernovae, the time delay does not matter for the supernova's internal evolution, because the entire event happens long before the light arrives, but the light curve still shows the event's progression as it occurred. In contrast, when observing a distant galaxy, the galaxy is seen as it was at one epoch, and the galaxy may have changed substantially since then. This is why astronomers talk about galaxy evolution by comparing populations at different redshifts, effectively comparing different times. The sky becomes a collection of time slices. A deeper effect appears when considering the medium light travels through. Space between galaxies is thin but not perfectly empty. Light can be absorbed or scattered by gas and dust. Dust grains can redden and dim light because they scatter shorter wavelengths more efficiently. Gas can absorb specific wavelengths associated with atomic transitions. This produces absorption lines in spectra. The pattern of absorption lines along the line of sight can reveal the distribution of gas between the source and the observer. For example, neutral hydrogen absorbs ultraviolet light at a specific wavelength, and when this absorption is seen at different redshifts, it reveals gas clouds at different distances. This turns light travel into a probe of intervening matter, not just of the source. It also shows that distance measurements require corrections, because intervening material can make a source appear dimmer than it would in a perfectly transparent universe. Astronomers account for this by observing in multiple wavelengths, and by modelling dust and gas effects. The point for intuition is that the signal carries both source information and path information. At large distances, the path can matter as much as the origin. Another important aspect of light travel time is that it limits how quickly information can move across cosmic structures. In a galaxy cluster, signals take millions of years to cross from one side to the other. In the cosmic web, signals take hundreds of millions of years to cross large voids. This means that cause and effect across such distances cannot be fast. Large-scale structures evolve slowly, not only because gravity acts gradually, but because information and influence cannot propagate faster than light. Even gravity's changes propagate at the speed of light, so the larger structures cannot coordinate rapid changes. This places an upper bound on the pace of cosmic evolution. The universe's size and the finite speed of signals enforce slow dynamics at large scales. This is part of why intuition can fail. Human experience is built on fast feedback and short distances. The cosmos is built on long delays and enormous separations. Yet these delays also create a scientific advantage. Because different distances correspond to different look-back times, the universe provides its own archive. A telescope does not need to travel to the early universe. It can observe it by collecting older light. This is why the cosmic microwave background is so valuable. It is light that has travelled since a very early epoch, carrying information about conditions that cannot be recreated easily in laboratories. It is also why very distant galaxies are valuable. They show star formation and structure at early times. The cost is that these objects are faint, because their light is spread out over huge distances and often has been stretched to longer wavelengths. Observing them requires sensitive instruments and long exposures. The practical limit of observation is not only the horizon set by time, it is also the faintness set by distance and by expansion. Light travel time also intersects with the expansion of the universe in a way that deepens the intuition challenge. When light travels through expanding space, the space stretches, the light increasing its wavelength. This changes the energy of the photons and shifts the light into redder wavelengths, often into infrared for very distant sources. This effect will be treated in the next region, but it is already present as a constraint. The farther the source, the more its light tends to be shifted and the harder it can be to detect with instruments designed for visible wavelengths. This is why infrared telescopes are crucial for studying early galaxies. The same principle explains why certain radio signals, such as the 21 centimeter line of neutral hydrogen, can be shifted to longer wavelengths, allowing different epochs of cosmic gas to be studied through radio observations. The overall picture of this region is simple and complete. Light travel time turns distance into a time delay. The sky becomes a map of the past. Signals are altered by what they pass through and by the expansion of space, and they become fainter as they spread. These constraints overwhelm everyday intuition, but they also provide the tools for cosmic measurement. By accepting that observation is delayed, and by treating delay as information rather than as a problem, science builds a stable ruler out of light itself. This completes the region of long travel held steady before moving to the specific measurement of expansion through redshift. With light travel time set as the basic link between distance and history, the next outer region is the stretching of light by the expansion of space. This stretching is observed as redshift, a shift of light to longer wavelengths. The word redshift comes from visible light, where longer wavelengths appear redder, but the same idea applies across all wavelengths. Redshift is one of the most important measurements in cosmology because it connects the light received today to the changing scale of the universe during the light's journey. It also challenges intuition because it requires treating space itself as dynamic. In daily life, space feels fixed and passive. In cosmology, space expands, meaning that the average distance between far unbound galaxies increases over time. This does not mean that objects expand in the same way. A galaxy does not swell with the expansion. A solar system does not grow. Gravity and other forces bind local systems strongly enough that they resist expansion. Expansion becomes important only when considering distances so large that local binding is negligible. Compared with the overall change in the cosmic scale factor, the parameter used to describe how the size of the universe changes with time. Redshift can be defined in plain terms by comparing the wavelength of a known spectral feature at emission with the wavelength observed at reception. Many atoms and molecules absorb or emit light at specific wavelengths determined by electron energy levels. These wavelengths are measured precisely in laboratories. When light from a distant galaxy is spread into a spectrum, these same patterns can be identified, but they appear at longer wavelengths. The ratio between observed and emitted wavelengths gives the redshift. A higher redshift means a larger stretching. In the expanding universe interpretation, this stretching occurs because the space through which the light travels expands, lengthening the light wave. If the universe expands by a certain factor, during the time the light travels, the wavelength is stretched by the same factor. The light does not lose its identity. It arrives with the same pattern, just shifted. This is why redshift is such a powerful tool. It preserves recognizable signatures while encoding the history of expansion. In addition to cosmic expansion, redshift can also occur from motion through space, as in the Doppler effect. When a source moves away, its light is shifted to longer wavelengths. When it moves toward the observer, it is shifted to shorter wavelengths. This effect is familiar in sound, where a moving siren changes pitch. In astronomy, Doppler shifts are used to measure motions of stars and galaxies. For nearby galaxies, Doppler motion can contribute significantly to observed redshift. But at large distances, the dominant contribution is the expansion of space. The difference matters because it shapes interpretation. In the expansion picture, redshift reflects the global behavior of the universe, not simply the motion of a galaxy through space. This is why the relationship between redshift and distance is not purely about velocity in a local sense. Instead, redshift indicates how much the universe has expanded since the light was emitted, which depends on the expansion history. The expansion history is described by parameters such as the Hubble constant, which sets the current rate of expansion, and by the contributions of matter radiation and dark energy to the overall dynamics. These parameters are inferred from multiple independent observations. One of the simplest relationships in cosmology is Hubble's law at relatively small redshifts, where the recessional velocity inferred from redshift is approximately proportional to distance. This relationship is what first revealed cosmic expansion. But at higher redshifts, the relationship becomes more complex because the expansion rate has changed over time. In the early universe, matter density is higher and gravity slows expansion. Later, dark energy becomes more influential, and expansion accelerates. The observation that expansion accelerates is supported by Type Ia supernova distance measurements, by patterns in the cosmic microwave background, and by large-scale structure data. What is known is that the combined data fit a model where dark energy behaves like a constant energy density of space within current measurement uncertainty. What remains uncertain is whether dark energy is truly constant, or whether it varies slowly with time, and whether there are subtle systematic effects in measurements that could shift inferred parameters. These uncertainties are constrained by ongoing surveys and improved calibration, but they remain a boundary in the current picture. Redshift also affects how objects are observed beyond shifting spectral lines. Because wavelength is stretched, the energy of each photon is reduced. This means that distant light is not only delayed and dimmed by distance, but also softened in energy by expansion. In addition, the expansion affects observed time intervals. A supernova light curve observed at high redshift appears stretched in time, with events unfolding more slowly in the observer's frame. This is called time dilation. It is a direct consequence of the same stretching factor that affects wavelengths. If the universe has expanded by a certain factor since the light was emitted, then the spacing between wave crests is stretched by that factor, and so are the time intervals between successive features in the signal. Observations of time dilation in distant supernovae provide evidence supporting the expansion interpretation over alternative explanations. In practical observing, redshift changes which instruments are needed. Light emitted in ultraviolet or visible bands can arrive as infrared. This is why infrared telescopes are essential for studying early galaxies and star formation in the young universe. It is also why certain spectral diagnostics move out of one band and into another as redshift increases. Astronomers must choose filters and spectrographs designed for the expected shifted wavelengths. This is not merely a technical detail, it is part of the reason intuition struggles. The same object type can look different at different redshifts, because the observed wavelengths correspond to different parts of its spectrum. A distant galaxy observed in one band may show mostly young stars, while the same galaxy observed in another band might reveal older stars or dust emission. Interpreting what is seen requires understanding which rest frame wavelengths are being sampled. This is one reason multi-wavelength observations are so valuable. Redshift also affects the apparent distribution of objects. Because the universe evolves over time, galaxies at high redshift are not simply farther versions of nearby galaxies. They are earlier versions, often smaller, more gas-rich, and more actively forming stars. The cosmic star formation rate, meaning the average rate of star formation per unit volume of the universe, rises to a peak at intermediate redshift, and then declines toward the present. This pattern is inferred from many observations and reflects how gas supply galaxy growth and feedback processes change over time. What is known is that star formation history has this broad rise and fall. What remains uncertain is the detailed contribution of different galaxy types at each epoch, and how dust obscuration affects inferred rates. Redshift, therefore, is not only a ruler, it is also a timestamp. It allows objects to be placed on a timeline of cosmic evolution. Another aspect of redshift is gravitational redshift, where light loses energy climbing out of a gravitational well, shifting to longer wavelengths. This effect is significant near very massive and compact objects like neutron stars and black holes, and it is also measurable in some contexts in the solar system. At cosmological distances, gravitational redshift from local potentials is generally small compared with expansion redshift, but it can contribute in detailed measurements of galaxy clusters and large-scale structure. The presence of multiple redshift mechanisms is a reminder that the universe is layered in effects, and careful measurement distinguishes them. The main cosmic redshift, however, remains the stretching of space during light's travel. This region is complete when the meaning of redshift is held steadily a measurable shift in wavelength that encodes the expansion of space, the passage of time, and the energy change of photons. It is a simple observation with deep consequences linking the light that arrives now to the size of the universe when the light began its journey. It turns distance into a record of expansion and makes the universe's growth measurable without leaving Earth. With redshift established, the next outward structure can be described as the patterned distribution of matter that redshift surveys reveal the web of filaments and voids that occupies the expanding space. With expansion measured through redshift, the next outer region is the large-scale pattern of matter, revealed when many redshifts and positions are mapped together. This pattern is often called the cosmic web. It is not a decorative name. It is a description of how galaxies and gas are arranged in a network of dense nodes connected by long filaments, with wide underdense regions between them called voids. The web emerges from gravity acting on small initial density differences over billions of years within an expanding universe. At this scale, size can overwhelm intuition because the structures are not single objects with boundaries. They are patterns spread across hundreds of millions of light years, and they are mostly made of empty space. The density contrasts are real, but the absolute densities are low by everyday standards. This combination of structure and emptiness is one of the strongest challenges to intuitive thinking about size. The cosmic web is inferred from surveys that map galaxies in 3 dimensions. A survey measures the position of each galaxy on the sky and its redshift. Position gives angular coordinates. Redshift gives distance in a cosmological model, and therefore gives a 3-dimensional location. When many galaxies are plotted, they do not fill space uniformly. They cluster. Clustering is not only an aesthetic impression, it can be quantified by statistics that measure the probability of finding galaxy pairs at a given separation compared with a random distribution. These statistics show that galaxies are more likely to be near other galaxies than a uniform distribution would predict. On small scales, galaxies gather in groups. On larger scales, groups gather into clusters and superclusters. Filaments connect these dense regions, forming bridges of galaxies and gas. Voids occupy the spaces between. This pattern is also traced by gas, especially hydrogen. Even where there are few galaxies, there can be diffuse gas that absorbs light from background sources. Quasar spectra with their many absorption lines reveal this gas distribution along the line of sight. Gravitational lensing adds another layer of evidence by mapping mass directly. In weak lensing, the shapes of background galaxies are subtly stretched by the gravity of intervening mass. By statistically analysing these shape distortions over large areas of sky, astronomers reconstruct maps of projected mass density. These maps align with the galaxy distribution, confirming that the web is not only a web of light, but a web of mass dominated by dark matter. Dark matter is the main scaffolding because it interacts through gravity and forms large structures earlier than ordinary matter can. Ordinary matter in the form of gas falls into the gravitational wells created by dark matter, cools and forms stars and galaxies. The result is that luminous galaxies trace the underlying dark matter distribution, but with bias, meaning galaxies do not perfectly match the mass distribution everywhere. This bias depends on galaxy type and environment, yet the broad correspondence remains strong. At the scale of clusters, the densest nodes of the web, the environment is extreme compared with the spaces between galaxies. A galaxy cluster contains hundreds to thousands of galaxies bound by gravity. Between the galaxies is hot gas at temperatures of millions of degrees emitting X-rays. The gas is heated by gravitational collapse and by shocks as matter falls into the cluster's potential well. This intracluster medium contains a large fraction of the ordinary matter in the cluster, often more than the stars themselves. The cluster also contains a much larger mass of dark matter, inferred from galaxy motions and lensing. The overall cluster potential well is deep, and the escape velocity can be high. Yet even in a cluster, most of the volume is empty space between galaxies. Galaxies rarely collide directly, though they can interact gravitationally and merge. The cluster environment can strip gas from galaxies as they move through the hot medium, a process called Ram pressure stripping. This can reduce star formation in those galaxies. The cluster also supports turbulence and sound-like waves in the hot gas, and it can host central supermassive black holes whose jets inject energy into the surrounding medium, affecting cooling. These are complex processes, but at this region the cluster serves mainly as an example of a dense node within a larger network, showing how matter concentrates in certain places while leaving vast gaps elsewhere. Filaments are the bridges between nodes. They can extend for tens to hundreds of millions of light years. They contain galaxies, groups, and diffuse gas. The gas in filaments can be warm-hot, meaning at temperatures of hundreds of thousands to millions of degrees heated by shocks as it accretes. This warm-hot intergalactic medium is thought to contain a significant fraction of the ordinary matter in the present universe, sometimes described as the missing baryons problem, where baryons are the particles that make up ordinary matter. Observations suggest that many baryons are not in stars or cold gas, but in these diffuse warm-hot regions that are difficult to detect. What is known is that multiple lines of evidence indicate a large reservoir of ordinary matter outside galaxies. What remains uncertain is the precise distribution and temperature structure of that gas, and the best methods for detecting it across the full range of environments. Filaments are therefore both visible through galaxies and partly invisible through diffuse gas, and they are vital for understanding how galaxies are fed. Gas can flow along filaments into galaxies, replenishing the fuel for star formation. In this way, the web is not only a static pattern, it is a flow network over long time guiding matter into deeper gravitational wells. Voids are the large underdense regions. They can be tens to hundreds of millions of light years across. Within a void, the density of galaxies is far below the cosmic average. Yet voids are not perfectly empty. They can contain faint galaxies, low-density gas, and dark matter. Their defining feature is relative emptiness compared to the surrounding filaments and nodes. Over time, as matter drains into denser regions, voids become more underdense. The expansion of space continues everywhere, but within voids where gravity from local mass concentrations is weaker, expansion can dominate more strongly. This can make voids expand faster than average, in the sense that their volume grows relative to denser regions. This is a subtle but important point. The web evolves not only by matter moving, but also by the geometry of expansion interacting with density. Voids, therefore, are dynamic regions that grow and change shape over cosmic time. They are also useful for cosmology because their large, low-density environments provide tests of gravity and expansion that are less affected by complex astrophysical processes inside galaxies. The cosmic web is a product of initial conditions and physical laws, but it also contains complexity that challenges intuition in a specific way. The web is mostly empty space. The filaments and clusters contain matter, but their filling factor, the fraction of volume they occupy, is small. A person might expect that structure means most of space is filled with something substantial. In the universe, structure means the opposite. A small fraction of space contains most of the matter, and most of space contains almost nothing. This is not a metaphor. It is a quantitative statement about densities and volumes. It also means that when imagining the universe, darkness and emptiness are the norm, and luminous islands are sparse. The web's pattern is real, but it is drawn on a vast canvas of near vacuum. The timescales of change at this scale are enormous. Filaments form and thicken over billions of years. Clusters grow by accreting groups and merging with other clusters. Voids expand and empty over similar times. The web's evolution can be studied by observing different redshifts which correspond to different epochs. At high redshift, the web is less mature. Galaxies are more actively forming stars and massive clusters are rarer. Over time, structure grows and the present web becomes more pronounced. Numerical simulations using gravity and gas physics reproduce this broad evolution when started from early conditions consistent with the cosmic microwave background. This agreement between simulations and observations supports the gravitational growth picture. Uncertainty remains in the details of how galaxies form and how feedback from stars and black holes affects gas, but the large-scale web pattern is robust. Completing this region means holding the cosmic web as the dominant large-scale structure, a network of nodes and filaments with immense voids between shaped by gravity in an expanding universe traced by galaxies, gas and lensing. It is the outer architecture within which smaller structures like individual galaxies sit as more compact islands. The next step inward will leave this web pattern and focus on those islands where size becomes more manageable, but still far beyond ordinary intuition. Within the cosmic web, the next inward region is the individual galaxy, a bound system that gathers stars, gas dust, and dark matter into a coherent structure. A galaxy is smaller than a filament or a cluster, but it is still immense. It can contain billions of stars, and its scale is measured in tens of thousands to hundreds of thousands of light years. Intuition often treats a galaxy as a crowd of stars packed close together, but the reality is mostly empty space. The typical distance between stars is large compared with stellar sizes. The galaxy's visible form is shaped by how its matter is distributed and how it moves under gravity. In this region, size becomes more concrete because galaxies have shapes and measurable rotation, yet they still overwhelm simple imagination because their boundaries are gradual and their main mass component is not directly visible. Galaxies are commonly described by broad morphological types. Spiral galaxies have flattened rotating disks with spiral arms. Elliptical galaxies have more rounded shapes with stars on more random orbits. Irregular galaxies lack a stable, symmetrical form, often because of interactions, or because they are small and dominated by localized star-forming activity. These categories reflect differences in angular momentum gas content and merger history. A spiral disk suggests that a large portion of the galaxy's stars share a common plane and rotate in an ordered way. Ellipticals often reflect past mergers that disrupted disks and randomized stellar orbits, yet the categories are not rigid. Many galaxies show both disk and bulge components, and many show signs of past interactions. The scale of a galaxy is often described by its visible stellar extent, but that extent depends on surface brightness, which fades gradually with distance from the center. A galaxy does not have a hard edge like a solid sphere. The density of stars decreases outward, and faint stellar halos can extend far beyond the bright disk. Beyond the stars, dark matter halos extend farther still. Dark matter is inferred from its gravitational influence. In a spiral galaxy, the orbital speeds of stars and gas can be measured as a function of distance from the center. If the mass were concentrated mostly where the light is, orbital speeds would tend to decline at large radii. Instead, many galaxies show rotation curves that remain roughly flat, meaning orbital speed stays nearly constant over a wide range. This indicates that mass continues to increase with radius, requiring a large halo of unseen mass. Gravitational lensing also supports this, showing mass distributions that exceed what stars and gas can account for. What is known is the general existence of dark matter halos around galaxies and their dominant contribution to galactic mass. What remains uncertain is the exact density profile of halos in small galaxies and the detailed nature of dark matter particles. These uncertainties are important for fine details, but they do not change the main idea. Galaxies are embedded in much larger gravitational structures than their light alone suggests. The internal structure of a typical spiral galaxy can be described in layers. Near the center is the bulge, a dense region of stars often older on average than disk stars. In many galaxies, including the Milky Way, a supermassive black hole resides at the center. Its presence is inferred from the motions of stars and gas very close to the center. When matter falls into such a black hole, it can release large amounts of energy, forming an active galactic nucleus. Not all central black holes are active at a given time. Activity depends on the supply of gas and the dynamics of accretion. Around the bulge is the disk, a flattened region containing stars, gas, and dust. Spiral arms are regions of enhanced density moving through the disk, compressing gas and triggering star formation. They are patterns that persist, not fixed material structures. Stars drift in and out of them while the pattern can remain. Above and below the thin disk is a thicker disk component containing older stars with orbits that take them farther from the plane. Surrounding the galaxy is a stellar halo sparse but extended, containing old stars and globular clusters. Globular clusters are dense spherical collections of stars, often very old, orbiting in the halo. The halo and clusters preserve clues about early galaxy formation and about mergers, because stars stripped from smaller galaxies can form streams and substructures in the halo. These streams can be detected by their coherent motions and compositions. The presence of such streams shows that galaxies grow by accretion of smaller systems over time. Mergers are a major driver of galaxy evolution. When two galaxies pass near each other, tidal forces can stretch them, pulling out long tails of stars and gas. If they merge, their stars usually do not collide directly, because the distances between stars are so large. Instead, the galaxy's overall gravitational potentials interact and their gas clouds can collide and shock. This can trigger bursts of star formation as gas is compressed. Over time, the merged system can settle into a new shape. Major mergers between similar mass galaxies can disrupt disks and produce more spheroidal systems, often resembling ellipticals. Minor mergers can thicken disks and add stars to halos without fully destroying the disk. This hierarchical growth is consistent with the cosmic web environment, where galaxies are fed by filaments and encounter neighbors in groups and clusters. A galaxy's gas content is central to its visible behavior because gas fuels star formation. Cold molecular gas, often found in giant molecular clouds, is the primary reservoir for forming new stars. In spiral galaxies, this gas tends to be concentrated in the disk, especially along spiral arms. In many elliptical galaxies, cold gas is scarce, and star formation rates are low. Yet ellipticals can contain hot gas halos detectable in X-rays, and they can acquire new gas through mergers. Star formation is a process of collapse and fragmentation within dense gas clouds. When gas becomes dense enough, gravity overwhelms internal pressure and turbulence in localized regions, forming protostars. Over time, protostars heat and ignite fusion, becoming main sequence stars. Massive stars form quickly and emit intense ultraviolet radiation that ionizes surrounding gas, creating bright regions called H2 regions, meaning regions of ionized hydrogen. These regions mark recent star formation. Massive stars also end their lives in supernova explosions, injecting energy and heavy elements into the interstellar medium. This feedback can both trigger and suppress further star formation by compressing nearby clouds or by heating and dispersing gas. The balance of feedback is complex and depends on environment. What is known is that feedback plays a major role in regulating star formation and shaping galaxy evolution. What remains uncertain is the detailed efficiency of feedback processes across different galaxy masses and epochs, and how black hole activity couples to gas on large scales. Chemical enrichment is another aspect that ties galaxy scale to smaller scales. The early universe is composed mostly of hydrogen and helium. Heavier elements are produced in stars and spread by stellar winds and supernovae. Over time, galaxies become enriched in these elements. This enrichment affects gas cooling and star formation, and influences the composition of planets that form later. In many galaxies, metallicity, meaning the abundance of elements heavier than helium, tends to be higher in central regions than in outer regions, reflecting more intense and longer star formation near the center and the inflow and outflow of gas. Spectroscopy allows metallicity gradients to be measured. Light from stars and gas carries line patterns that indicate element abundances. This is another example of how atomic scale properties become tools for measuring vast structures. A galaxy is therefore an object where multiple scales intersect the gravity of a massive dark halo. The rotation of a disk, the formation of stars in gas clouds, and the chemical evolution driven by stellar life cycles. Yet in this region, the focus remains on the galaxy as a coherent island within the cosmic web, defined by its structure, rotation, and layered components. Its size overwhelms intuition, but it becomes manageable through measurements, rotation curves, stellar distributions, gas maps, and lensing. This completes the galaxy region, setting the stage for the next inward step, where the galaxy's most important local landmarks, individual stars, become the focus. Within a galaxy, stars become the next inward scale where size is both overwhelming and measurable. A star is far smaller than a galaxy, yet it is still enormous compared to anything on Earth. A star is a self-gravitating sphere of hot plasma. Plasma is gas in which electrons are separated from nuclei, allowing the gas to conduct electricity and respond strongly to magnetic fields. A star shines because nuclear fusion in its core releases energy. Fusion joins light nuclei into heavier nuclei, converting a small amount of mass into energy. That energy moves outward and escapes as light and other radiation. The star's structure is maintained by balance. Gravity pulls inward and pressure from hot gas, and radiation pushes outward. This balance can persist for a very long time. At this scale, size begins to overwhelm intuition in a different way. A star's diameter can be many times larger than the diameter of a planet, yet the distance to the next star can be so large that the star still appears as a point of light. The neighborhood between stars is mostly empty, containing only thin gas and dust. This contrast between immense objects and vast separation is a recurring theme of size. Measuring the distance to stars begins with parallax. Parallax is the apparent shift in a nearby star's position against more distant background stars as Earth moves around the Sun. The baseline is the diameter of Earth's orbit. By observing the star at opposite points in Earth's orbit and measuring the tiny angle of shift distance can be calculated. This is a direct geometric method and forms the foundation of the stellar distance scale. As stars get farther away, the parallax angle becomes too small to measure reliably, and other methods are used. But parallax anchors them, turning starlight into a calibrated map. With distance known, a star's intrinsic brightness can be derived from its observed brightness. Intrinsic brightness, also called luminosity, is the total energy a star emits per unit time. Observed brightness depends on distance, and without distance, a bright star could be either nearby and modest or far away and powerful. This ambiguity is why size overwhelms intuition. The sky compresses three-dimensional space into a two-dimensional view. Measurement restores depth. Beyond parallax, standard candles extend distances. Certain stars vary in brightness with regular periods, and the period is linked to intrinsic brightness. Cepheid variable stars are an example. Their pulsation period correlates with luminosity. By measuring the period and observing the apparent brightness, distance can be estimated. Cepheids can be seen in nearby galaxies, helping link stellar distances to galactic distances. But in this region, the focus remains on stars as individual objects with measurable properties, not yet on whole systems of planets. A star's surface temperature can be inferred from its color and spectrum. A spectrum is light separated into wavelengths, revealing absorption lines, where certain wavelengths are removed by atoms in the star's atmosphere. Different elements absorb at characteristic wavelengths. The pattern of lines reveals composition, while the overall distribution of intensity across wavelengths reveals temperature. Hotter stars emit more short-wavelength light and appear bluer. Cooler stars emit more long-wavelength light and appear redder. Yet colour alone can be altered by dust between the star and the observer, so spectra and multi-wavelength observations are used to correct for reddening. Once temperature and luminosity are known, a star can be placed on a diagram of luminosity versus temperature. Most stars lie on the main sequence, a band where stars are stable, and fuse hydrogen in their cores. On this sequence, mass is the key parameter. More massive stars are hotter and more luminous, but they burn fuel faster and have shorter lifetimes. Less massive stars are cooler and dimmer, but they can live for extremely long times. This relationship between mass and lifetime is another place where size overwhelms intuition. A massive star can be dozens of times more massive than the Sun, and can live only a few million years, while a small red dwarf can be much less massive and can live far longer than the current age of the universe. The range of stellar lifetimes spans orders of magnitude, yet the underlying physics is stable luminosity rises steeply with mass, so fuel is consumed faster in massive stars. Stellar evolution describes how stars change over time. When a star exhausts hydrogen in its core, the balance changes. The core contracts and heats, and hydrogen fusion can continue in a shell around the core. The outer layers expand and cool, and the star becomes a giant. For stars like the Sun, later stages include helium fusion and the shedding of outer layers, leaving a dense core remnant called a white dwarf. A white dwarf is supported by electron degeneracy pressure, a quantum effect arising from the Pauli exclusion principle, which prevents electrons from occupying the same state. For more massive stars, fusion can proceed through heavier elements up to iron in the core. Iron fusion does not release energy, so the core collapses, leading to a supernova explosion. The remnant can be a neutron star or a black hole depending on mass. A neutron star is supported by neutron degeneracy pressure and nuclear forces, and it can have an extremely strong magnetic field. A black hole is a region where gravity is so strong that not even light can escape from within a boundary called the event horizon. What is known is the broad sequence of stellar evolution and the existence of these remnants supported by observations of star clusters, supernova remnants, white dwarfs, neutron stars, and black hole candidates. What remains uncertain in detail includes the precise mass boundaries between outcomes and the role of rotation and magnetic fields in the most massive stars, but the overall framework is consistent. Stars also shape their environment through radiation and winds. The interstellar medium, the gas and dust between stars, is influenced by stellar ultraviolet light, which can ionize hydrogen, and by stellar winds, streams of charged particles flowing outward. Supernovae inject enormous energy, driving shock waves that compress and heat gas. These shocks can trigger the collapse of nearby clouds, promoting star formation, or they can disperse clouds, suppressing star formation. This feedback creates a cycle. Stars form from gas live and modify the gas die and return material and energy, and the gas forms new stars. The chemical elements heavier than helium are produced in stars and spread through winds and explosions. This enrichment enables rocky planets and complex chemistry later. In the context of size, this cycle shows how a star's influence extends far beyond its physical surface. The star is a compact object, but its radiation field and winds fill a region around it. Yet even this region is small compared to the distances between stars on galactic scales. In the Sun's neighbourhood, the nearest star is more than 4 light-years away. That distance is enormous compared to the size of the Sun. This means that stellar systems are isolated islands of gravity and light separated by vast emptiness. The emptiness is not truly empty, but it is thin enough that direct interactions between stars are rare except in dense star clusters or near galactic centres. This separation allows stellar evolution to proceed largely independently for most stars. In clusters, stars can interact more, exchanging companions or colliding in rare cases, but even there the distances are large compared to stellar diameters. Stars serve as calibrators of size because their spectra reveal physical conditions, and their brightness with distance reveals luminosity. They also serve as clocks because their lifetimes depend on mass, and populations of stars reveal the age of clusters and galaxies. In this region, the key is to hold the star as a measurable object that still overwhelms intuition a sphere of plasma where fusion provides steady energy, where gravity and pressure balance, where size spans a wide range, and where the distance to neighbouring stars is vast. This completes the stellar region as a distinct inward step preparing the ground for the next region, where the focus narrows to the organised orbits and formation processes of planetary systems around stars. Around many stars, gravity shapes a smaller architecture that can overwhelm intuition in a more familiar way because it resembles motion seen in the sky. Planets, tracing paths, moons, circling planets, and smaller bodies moving in elongated orbits. A planetary system is a family of objects bound to a star held together by gravity and arranged by the physics of formation and long-term orbital dynamics. Compared with a star, the system is spread out. Compared with the distances between stars, it is compact. This contrast is central. A planetary system can feel large when thinking about distances between planets, yet it occupies a tiny island within interstellar space. The same sense of size that overwhelms intuition at cosmic scales also appears here as nested proportion. The star is huge, the orbits are wide, and the gap to the next star is wider still. The formation of a planetary system begins in a protoplanetary disk. When a star forms from a collapsing cloud of gas and dust, angular momentum causes the infalling material to flatten into a rotating disk around the young star. This disk contains gas, mostly hydrogen and helium, and solid grains made of heavier elements and compounds. In the disk, tiny dust grains collide. Some collisions lead to sticking, forming larger aggregates. Through many steps, these aggregates can become larger bodies called planetesimals. Once bodies become large enough, gravity helps them grow faster by attracting more material. This stage can lead to protoplanets, which can merge and clear paths in the disk. The disk does not last long by cosmic standards. Observations of young stars show that disks typically disperse in a few million years. The dispersal happens through accretion onto the star through winds driven by radiation and magnetic fields, and through the formation of planets that carve gaps and alter flows. This means that giant planets that require large gas envelopes must form while gas remains abundant. Rocky planets can continue growing through collisions after the gas is mostly gone, but their growth also begins during the disk phase. The disk's temperature and composition vary with distance from the star. Near the star, temperatures are high, and only refractory materials, meaning materials that can remain solid at high temperature, can exist as solids. These include metals and silicate minerals. Farther out, temperatures are lower and volatile substances like water, carbon dioxide, and ammonia can condense as ice. The boundary where water transitions from vapor to solid is often called the snow line. Beyond the snow line, the amount of solid material available increases because ice adds mass. This makes it easier to build large solid cores quickly. These cores can then attract hydrogen and helium gas from the disk-forming gas giants. This framework helps explain the basic structure of the solar system, with rocky planets closer in and giant planets farther out. However, exoplanet discoveries show that systems often do not follow the solar system's layout. Many systems contain large planets very close to their stars. This implies that planets can migrate after forming. Migration is orbital change driven by interactions. In the disk phase, a planet's gravity interacts with the disk's gas, creating waves and exchanging angular momentum. Depending on the planet's mass and disk properties, the planet can spiral inward or outward. After the disk disperses, planets can continue to shift through gravitational interactions with each other. Instabilities can occur, leading to close encounters, scattering, and even ejection of planets into interstellar space. These processes create the wide variety of observed exoplanet architectures. What is known is that migration and dynamical reshaping are necessary to explain many observed systems, including hot Jupiters, which are giant planets on very close orbits, and compact multi-planet systems with several planets within orbits smaller than Mercury's orbit in the solar system. What remains uncertain is which migration pathways dominate in different systems and how common each history is. Yet the broad lesson is stable planetary systems are not fixed at birth. They can be rearranged by gravity. Orbital mechanics provides the language of this region. A planet's orbit is described by its size, shape, and orientation. In the simplest case, a planet follows an ellipse with a star at one focus. The closer the planet is to the star, the faster it moves and the shorter its orbital period. These relationships arise from gravity and the conservation of angular momentum. In systems with multiple planets, gravity between planets introduces additional effects. Orbits can precess, meaning the ellipse slowly rotates. Planets can exchange angular momentum, causing small changes in orbital elements. In some cases, planets become locked in resonances where their orbital periods form simple ratios such as 2:1 or 3:2. Resonances can stabilize systems by preventing close encounters, or they can destabilize them by amplifying orbital eccentricities depending on circumstances. Eccentricity describes how stretched an orbit is. A circular orbit has low eccentricity. A highly elongated orbit has high eccentricity. Many exoplanets have higher eccentricities than planets in the solar system, indicating past dynamical interactions. Inclination, the tilt of an orbit relative to a reference plane, can also vary. Some exoplanet systems show misalignment between planetary orbits and the star's rotation axis, suggesting past perturbations. These features show that the calm clockwork image of planets in neat flat circles is not always correct. Gravity produces order, but it can also produce chaos when multiple bodies interact strongly. The measurement of planetary systems around other stars relies on subtle signals. The transit method detects periodic dips in a star's brightness when a planet passes in front of the star. The depth of the dip reveals the planet's size relative to the star. The timing reveals the orbital period. The shape of the transit can reveal orbital inclination, and with repeated high-quality observations can reveal additional planets through slight timing variations. The radial velocity method detects the star's motion toward and away from the observer, caused by the planet's gravitational pull. This motion shifts the star's spectral lines through the Doppler effect. The amplitude of the shift reveals the planet's minimum mass. Combining transit and radial velocity measurements yields both mass and radius, and therefore density, a key clue to composition. Direct imaging can detect planets by blocking or subtracting the star's light, usually for young massive planets far from their stars. Microlensing detects planets through temporary brightening caused by gravitational lensing of a background star when a foreground star with a planet passes near the line of sight. Each method has biases, detecting certain kinds of planets more easily than others. Together they reveal that planets are common and that system architectures are diverse. Within a planetary system, smaller bodies also matter. Asteroids are rocky remnants often concentrated in belts or scattered populations. Comets are icy bodies that can have long elliptical orbits, sometimes originating from distant reservoirs. In the solar system, the asteroid belt lies between Mars and Jupiter, and beyond the outer planets lies a region of icy bodies including the Kuiper belt, and a more distant cloud of comets inferred from long-period comet orbits. These reservoirs preserve material from the early solar system. Comets can deliver water and organic molecules to inner regions through impacts, though the relative importance of comet delivery versus other sources remains an area of study. The known point is that small bodies contain primitive material, and that impacts have shaped planetary surfaces. The uncertain point is the detailed contribution of different reservoirs to volatile delivery in each system. Moons are another major component. Many planets have moons formed through different pathways accretion in a disk around a planet capture of passing bodies or giant impacts. Earth's moon is widely thought to have formed from a giant impact early in Earth's history, leading to a debris disk that accreted into the moon. In the outer solar system, many large moons formed in disks around the giant planets. Some moons, like Europa and Enceladus, show evidence of subsurface oceans and tidal heating. Tidal heating occurs when a moon is flexed by gravitational forces generating internal heat. This shows that a planetary system's dynamics can influence habitability conditions on moons as well as on planets. The scale of a planetary system is therefore not only spatial, but also energetic, with gravity shaping both orbits and internal heating. The main point of this region is that a planetary system is a compact hierarchy centered on a star built from a disk, sculpted by migration and interactions, and measured through subtle effects on starlight and stellar motion. It overwhelms intuition because it contains vast empty gaps between planets compared with their sizes, and because its diversity defies the expectation that the solar system's layout is typical. Yet, it remains grounded in stable physics, gravity conservation laws, collisions, and the thermodynamics of disks. This completes the planetary system region, preparing for the next step inward, where attention narrows from a family of orbits to a single world as a whole object. Within a planetary system, attention can narrow to a single planet as a whole world. This is the next inward region because it treats the planet as one bounded object with measurable bulk properties before moving into its thinner outer layers and deeper interiors. A planet is shaped primarily by gravity. If it is massive enough, gravity pulls it toward a rounded form. The planet's mass radius, average density, orbit rotation, and energy budget together define its basic character. These parameters are familiar words, but they can still overwhelm intuition, because the planet is simultaneously a compact sphere and a layered system, and its behavior depends on timescales that range from seconds to billions of years. Holding the planet as a whole is a way to steady scale before entering finer layers. Mass and radius are the most basic measures. Mass determines gravitational pull. Radius sets the size of the surface and the distance from the center where that gravity is felt. From mass and radius, average density can be calculated. Density is a clue to composition. A high average density suggests a large fraction of rock and metal. A low average density suggests a large fraction of gas or significant ice content depending on mass and environment. In the solar system, the inner planets are rocky and dense. The outer gas giants have lower average densities because they are dominated by hydrogen and helium, and the ice giants have compositions with large fractions of volatile compounds such as water, ammonia, and methane, often in fluid or high-pressure forms. Exoplanet measurements show many planets in between these categories, with sizes and masses suggesting rocky cores wrapped in thick envelopes of gas or water-rich planets with deep layers. What is known is that the mass-radius relationship allows broad classification. What remains uncertain for many exoplanets is the detailed internal layering because different mixtures can yield similar average densities. Yet the bulk parameters still set strong constraints and serve as the stable frame for a world. A planet's orbit sets how much energy it receives from its star. The incoming energy depends on the star's luminosity and the planet's distance. It also depends on albedo, the fraction of light reflected back to space by clouds, ice, or bright surfaces. The planet also emits energy as infrared radiation. Over long time, a planet's average temperature settles into a balance between absorbed incoming energy and emitted outgoing energy, modified by the atmosphere if one exists. This balance is not necessarily stable in detail. Seasonal changes, volcanic episodes, and variations in greenhouse gases can shift it. But as a global concept, radiative balance frames climate. Rotation adds another global dimension. Rotation sets day and night cycles and influences atmospheric circulation through the Coriolis effect. Rapid rotation tends to organize winds into bands and jets. Slow rotation allows larger day-night contrasts. Axial tilt, the angle between the rotation axis and the orbital plane, sets the strength of seasons. A planet with high tilt can have extreme seasonal variations, with one hemisphere receiving intense sunlight for part of the year and little for another. A planet with low tilt can have weaker seasons. These rotational parameters can be measured in the solar system directly. For exoplanets, some can be inferred from orbital properties and from observed phase curves, but often they remain uncertain. A special case occurs for close-in planets which can become tidally locked. Tidal locking happens when gravitational interactions between the planet and star create tides that dissipate energy and slow the planet's rotation until it matches the orbital period. The result is that the same side of the planet always faces the star, creating a permanent day side and night side. This configuration can create strong temperature contrasts that drive winds. Whether such a world can maintain stable conditions depends on atmospheric and oceanic heat transport, if those are present. What is known is that tidal locking is likely common for planets close to their stars, especially around small stars where habitable zone distances are close. What remains uncertain is the diversity of climates under these conditions across different atmospheric compositions and surface states. The planet's energy budget also includes internal heat. Internal heat comes from several sources: heat left over from formation, and impacts heat released as denser materials sink and lighter materials rise in differentiation, heat from radioactive decay of certain elements in rocks, and in some cases tidal heating. Internal heat drives geology. It can power volcanism, mantle convection, and tectonics, and it can maintain subsurface oceans in icy worlds. The amount of internal heat depends strongly on planet size and composition. Larger rocky planets cool more slowly because they have a smaller surface area relative to their volume, allowing them to retain heat longer. Smaller planets cool more quickly, potentially becoming geologically inactive earlier. This is why the Moon is geologically quiet today, and why Mars has much less active geology than Earth, though local activity may still occur. Yet size is not the only factor. Composition, water content, and the presence of insulating layers also matter. Tidal heating can be significant in certain moons and some close-in planets, maintaining internal activity even in smaller bodies. This shows that a planet's global behavior can be driven by both intrinsic properties and orbital context. Another global property is the magnetic field. A magnetic field is generated if the planet has a layer of electrically conducting fluid in motion, organized in a way that sustains a dynamo. For Earth, the outer core is liquid iron, and convection combined with rotation generates a strong global field. A magnetic field can influence how the atmosphere interacts with the stellar wind, which is a stream of charged particles flowing outward from the star. It can reduce atmospheric erosion in some contexts, though not all atmospheric loss is prevented by a field, and some planets without strong fields can still hold thick atmospheres. The presence or absence of a field depends on internal structure and thermal history. For exoplanets, direct detection of magnetic fields is difficult, so fields are often inferred indirectly or remain unknown. Still, the field is a global feature that can extend far beyond the planet, creating a magnetosphere that occupies a volume much larger than the planet itself. This adds a subtlety to size. The planet's influence is not limited to its solid body. Its gravity, atmosphere, and magnetic field define extended domains that interact with space. A planet also changes over time. Its orbit can shift through interactions. Its rotation can slow through tides. Its interior can cool. Its atmosphere can be gained or lost. Its surface can be resurfaced by volcanism or shaped by impacts and erosion. The timescales differ. Impacts can change a surface in seconds. Atmospheric loss can occur over millions to billions of years. Interior cooling unfolds over billions of years. This range of timescales can overwhelm intuition because it compresses slow and fast processes into one object. A calm way to handle this is to hold the planet as a system in long-term evolution, where present conditions are a snapshot in a long sequence. Evidence for this evolution comes from surface craters, rock ages, atmospheric composition, and isotopic ratios. Isotopes are atoms of the same element with different numbers of neutrons. Some isotopic ratios change through radioactive decay and can be used as clocks. Others shift through atmospheric escape or chemical processes, leaving fingerprints of history. For example, the ratio of certain isotopes in an atmosphere can indicate how much lighter gases escaped over time, because lighter isotopes escape more easily. These tools connect atomic scale differences to planet scale evolution. Observing exoplanets as whole worlds is challenging but increasingly possible. Transits yield radii. Radial velocities yield masses. Together they give density. Transit spectroscopy can reveal some atmospheric features which then influence interpretations of temperature and composition. Phase curves can reveal day-night temperature differences and heat transport. For some directly imaged planets, spectra reveal atmospheric composition and cloud properties, yet most exoplanets remain known primarily by a few bulk parameters. Even so, those parameters define the planet as a whole object. They allow comparisons across many systems, revealing how common different kinds of worlds may be. The planet level is therefore a bridge between cosmic scale and local physical experience. It is large enough to be shaped by gravity into layers and to maintain long-term cycles, yet small enough to be a single coherent sphere. It overwhelms intuition because the world's mass energy flows and timescales exceed human experience, and because its extended domains of atmosphere and magnetism expand its effective presence beyond the solid surface. This region is complete when the planet is held as a whole, a rounded body with mass radius density, orbit rotation, internal heat, and possible magnetic influence set within the star's radiation field. The next inward step will move from the planet as a whole to the planet's thin outer shell of gas, where pressure and temperature gradients create an atmosphere that strongly shapes surface reality. Around a rocky planet, the atmosphere is the next inward region, because it is the first physical layer encountered above the surface, and because it strongly shapes what a planet feels like despite being thin compared with the planet's radius. The atmosphere is a shell of gas held by gravity thickest near the surface and thinning rapidly with height. It is where pressure, temperature, chemistry, and motion interact, producing weather and climate. Intuition often treats air as empty space, but at the scale of a planet, air is a material layer with weight, heat capacity, and chemical activity. Its thinness compared with planetary size is part of what overwhelms intuition. A planet can be thousands of kilometers in radius, while the region containing most of the atmosphere's mass can be only tens of kilometers thick. Yet that small fraction can determine whether liquid water can exist on the surface, whether rocks are weathered, and how much radiation reaches the ground. Pressure is the first key property. Atmospheric pressure is the force per area exerted by gas molecules colliding with the surface. Gravity pulls the gas downward, so pressure is highest near the surface and decreases with altitude. The decrease is steep because each higher layer has less gas above it. The exact rate depends on temperature and on the average mass of atmospheric molecules. Warmer air has faster moving molecules and spreads out more, giving a larger scale height. Lighter gases also have larger scale heights, while heavier gases stay closer to the surface. This is why hydrogen tends to be found higher in an atmosphere, and why planets with weak gravity can lose hydrogen more easily. The relationship between gravity, temperature, and molecular mass sets the overall vertical structure. Temperature in an atmosphere is shaped by radiation and by motion. Sunlight can be absorbed directly by gases and particles heating certain layers. Sunlight also warms the surface, which then emits infrared radiation upward. Some gases absorb infrared radiation, trapping heat and warming the lower atmosphere. This is the greenhouse effect. It occurs because certain molecules, especially those with 3 or more atoms or with asymmetric structure, have vibrational modes that interact strongly with infrared wavelengths. Water vapor, carbon dioxide, methane, and nitrous oxide are key examples on Earth. The greenhouse effect is not a single switch. It depends on gas concentrations, cloud cover, and how heat is transported by winds and convection. It can be mild as on Earth, or extreme as on Venus, where a dense carbon dioxide atmosphere and thick cloud layers produce very high surface temperatures. What is known is that greenhouse warming follows from molecular absorption and radiative transfer, and it can be modelled with well-tested physics. What remains uncertain in many cases is the detailed role of clouds and aerosols, because they can both reflect sunlight cooling the surface and trap infrared radiation warming it. Their net effect depends on particle size, altitude, and coverage. The vertical layering of an atmosphere can be described by how temperature changes with height. On Earth, the lowest layer is the troposphere, where temperature generally decreases with height, because the surface is the main heat source, and rising air expands and cools. The troposphere is where most weather occurs, driven by convection, moisture, and winds. Above it is the stratosphere, where temperature increases with height, because ozone absorbs ultraviolet light heating that layer. Higher still are the mesosphere and thermosphere, where different absorption processes dominate. Other planets have different layer structures. Mars has a thin atmosphere with strong daily temperature changes near the ground. Venus has a thick atmosphere with a very strong greenhouse effect and dense cloud layers. Titan has a thick nitrogen atmosphere with methane and haze. Gas giants have deep atmospheres where pressure increases downward and where cloud layers form at different depths depending on temperature and chemistry. The specific names of layers may differ, but the organizing principle is the same. Temperature gradients reflect where energy is absorbed and where it is emitted. Atmospheric circulation arises because energy input is uneven. The equator receives more sunlight than the poles. The day side receives more than the night side. These differences create pressure gradients that drive winds. Rotation bends these winds through the Coriolis effect, producing curved flow patterns. On Earth, this creates trade winds, jet streams, and rotating storms. On Jupiter and Saturn, rapid rotation and deep atmospheres produce strong banded jets and long-lived vortices. On tidally locked exoplanets, the strongest gradient can be between day and night, potentially producing strong winds and distinctive hotspot offsets seen in thermal phase curves. The speed and pattern of winds depend on atmospheric thickness, rotation rate, and the presence of oceans or continents that store and redistribute heat. Moisture and phase changes add another layer. On Earth, water can exist as vapor, liquid, and ice under surface conditions. Evaporation cools the surface and adds water vapor to the air. Condensation releases latent heat, warming the surrounding air and fueling storms. Precipitation returns water to the surface. This cycle transports heat and shapes clouds. On other worlds, similar cycles can occur with different substances. Titan's methane can evaporate and condense, producing methane rain and lakes. On Venus, sulfuric acid droplets form clouds. These cycles show that atmospheres are not only gases but also suspended liquids and solids. Aerosols, meaning small particles in the air, can come from volcanic eruptions, dust storms, sea spray, or chemical reactions in the upper atmosphere. Aerosols scatter and absorb sunlight and can alter cloud formation. Atmospheric chemistry is driven by sunlight, by surface interactions, and by internal sources like volcanism. Ultraviolet light can break molecules apart, producing reactive fragments that recombine into new compounds. Oxygen and ozone chemistry on Earth is shaped by such photochemical processes. On Titan, ultraviolet light and charged particles drive complex organic haze formation. The composition of an atmosphere is therefore not only what was initially outgassed or captured, it is also what is continually transformed. Atmospheric escape removes gases over time. Escape can be thermal, where molecules in the upper atmosphere have enough speed to leave, or non-thermal, where charged particles and radiation energize atoms and molecules and carry them away. Lighter gases escape more readily. Planets closer to active stars can experience stronger atmospheric loss, especially if their gravity is weak. Over geological time, escape can change an atmosphere's composition and thickness. The history of water can be especially important. If a planet loses water by breaking water vapor into hydrogen and oxygen in the upper atmosphere and losing hydrogen to space, the remaining oxygen can react with rocks or accumulate depending on conditions. This means that atmospheric composition can reflect long-term evolution, not just present processes. Measurement of atmospheres depends on how they interact with light. For the solar system, probes and landers can measure pressure and composition directly. For exoplanets, most information comes from spectroscopy during transits and eclipses. During a transit, some starlight passes through the planet's atmosphere, and certain wavelengths are absorbed more than others, creating a transmission spectrum. During a secondary eclipse, when the planet passes behind the star, the drop in combined light can reveal the planet's emitted and reflected spectrum. Phase curves track brightness over an orbit, revealing temperature contrasts and heat transport. These methods are challenging. Signals are small, and clouds and hazes can flatten spectra, hiding specific gas features. Yet progress has been steady, with detections of water vapor, carbon dioxide, sodium, and other species in some atmospheres, especially in hot, large exoplanets. The known point is that atmospheric characterization beyond the solar system is possible and improving. The uncertain point is the detailed composition and structure of many smaller planets, where signals are faint and confounding factors are strong. The atmosphere also connects directly to surface conditions. It controls surface pressure, which determines whether liquids can exist. It controls surface temperature through greenhouse effects and heat transport. It delivers weathering agents such as rain and wind, shaping landscapes. It also shields the surface from some radiation and small impacts. In this inward region, size overwhelms intuition because a thin layer can dominate a planet's habitability and appearance. The atmosphere is a skin, but it is an active skin with steep vertical gradients and strong horizontal flows. It is a place where molecules move freely, where energy is absorbed and emitted, where chemistry transforms, and where the planet meets space. This completes the atmospheric region as the planet's outer gas layer held steady before moving inward to the next layer, where liquid water, if present, forms another thin but powerful domain between air and rock. If a planet has oceans, they form the next inward region beneath the atmosphere, a layer where scale becomes vertical and pressure becomes a dominant change with depth. An ocean is a body of liquid that can cover a large fraction of a planet's surface, storing heat, dissolving gases, and moving in currents that redistribute energy and chemicals. On Earth, the ocean is made of water with dissolved salts, but the same physical ideas apply to other liquids on other worlds, such as methane and ethane on Titan. The ocean is thin compared with planetary radius, yet within that thin layer, conditions range from sunlit surface turbulence to cold, dark, high-pressure depths. Intuition often imagines an ocean as a uniform volume, but the reality is layered, structured, and constantly in motion. Light is the first boundary. Sunlight enters the upper ocean and fades with depth because water and dissolved substances absorb and scatter light. Different wavelengths fade at different rates, with red light absorbed quickly and blue light penetrating deeper in clear water. The surface layer, where enough light remains for photosynthesis, is called the photic zone. Below it is the aphotic zone, where light is too weak for photosynthesis. This matters because life and chemistry change with the availability of light. On Earth, most primary production in the ocean occurs near the surface through microscopic phytoplankton, which convert carbon dioxide into organic matter using light. Below the photic zone, organic matter produced above can sink, feeding deeper ecosystems, but new production is limited without light, except in places where chemical energy supports chemosynthesis. The depth of the photic zone varies with water clarity and with the amount of suspended particles. Coastal waters can be cloudy with sediments and plankton limiting light penetration. Open ocean gyres can be clearer, allowing light to reach deeper. The second boundary is temperature. The surface ocean is warmed by sunlight and cooled by contact with the atmosphere, evaporation and mixing. In many regions, temperature decreases sharply with depth across a layer called the thermocline. Below the thermocline, deep waters are often cold and more uniform in temperature. This pattern varies with latitude. Near the pole's surface, waters can be cold enough that the vertical gradient is weaker and mixing can reach deeper. Near the equator, strong heating can produce a stable, warm surface layer. Temperature affects density, and density differences create stratification. Colder water is generally denser than warmer water, and saltier water is denser than fresher water. The combined effect of temperature and salinity on density controls how easily water layers mix. Strong stratification can trap nutrients in deep water and keep surface waters nutrient-poor, limiting productivity. Weak stratification or active mixing can bring nutrients upward, supporting blooms. Salinity is shaped by evaporation, precipitation, river input, and ice processes. When seawater freezes, most salt is excluded from the ice, increasing the salinity and density of the surrounding water. This denser water can sink and contribute to deep water formation. When ice melts, it adds fresh water, reducing surface salinity and stabilizing stratification. These processes are central near polar regions and influence global circulation. Pressure increases steadily with depth. Each additional column of water adds weight, so pressure rises by about 1 atmosphere for every 10 meters on Earth, and continues to rise to extreme values in the deep ocean. High pressure changes the behavior of gases, increasing their solubility and affecting the stability of certain compounds. It also influences biological structures. Deep-sea organisms have membranes and proteins adapted to pressure. Pressure can also stabilize gas hydrates' crystalline structures, where gas molecules are trapped in cages of water molecules, forming in seafloor sediments under specific temperature and pressure conditions. Methane hydrates are an example. Their stability links the deep ocean to carbon storage and to potential release under warming or pressure changes. Ocean circulation is driven by wind, by density differences, and by tides. Winds push surface waters, creating currents and gyres. Because the planet rotates, the Coriolis effect deflects moving water, producing large-scale rotating systems in ocean basins. Along coasts, winds can drive upwelling where surface water is moved away, and deeper water rises to replace it. Upwelling brings nutrients to the surface, supporting high biological productivity. Downwelling can push oxygen-rich surface water into deeper layers, helping ventilate the deep ocean. Density-driven circulation, called thermohaline circulation, involves the sinking of cold, salty water at high latitudes and the slow return flow of deep water through the global ocean. It is not a single, simple conveyor belt, but a complex network of pathways and mixing processes. Still, the basic principle is stable density differences create vertical motions that connect surface and deep layers. The timescales differ. Surface currents can move quickly, changing over days to seasons. Deep circulation can take centuries to millennia for water to travel through the global system. This separation of timescales is another way ocean size overwhelms intuition. The surface seems active and immediate, while the deep ocean changes slowly, yet both are part of the same fluid body. Waves and tides add energy and mixing. Wind-generated waves affect the surface, breaking and driving turbulence that mixes the upper layer. Tides driven by gravitational forces mainly from the moon and the sun cause regular changes in sea level and generate strong currents in shallow seas and narrow passages. Tidal flow over seafloor topography can generate internal waves within the ocean interior. These internal waves can travel long distances and break mixing layers and contributing to the vertical transport of heat and nutrients. Even in regions that appear still, internal wave motion can be present. The ocean also exchanges gases and heat with the atmosphere. Carbon dioxide dissolves into seawater. In water, carbon dioxide reacts to form carbonic acid and then bicarbonate and carbonate ions, creating a buffering system that allows the ocean to store large amounts of carbon. Increased carbon dioxide uptake can increase acidity, affecting organisms that build shells and skeletons from calcium carbonate. Oxygen enters the ocean from the atmosphere and from photosynthesis near the surface. It is consumed by respiration and decomposition of organic matter. In some regions, oxygen levels drop at intermediate depth, forming oxygen minimum zones. These zones are influenced by circulation temperature and productivity. As the ocean warms, oxygen solubility decreases and stratification can increase, potentially expanding low oxygen regions. The exact future patterns depend on circulation changes and biological responses, but the physical tendency is clear. Heat exchange is equally important. The ocean stores large amounts of heat and can transport it through currents. This moderates climate and influences weather patterns. On Earth, phenomena such as El Niño reflect shifts in the ocean atmosphere, coupling altering wind patterns, sea surface temperatures and rainfall. These coupled systems show that the ocean is not passive. It interacts with the atmosphere in feedback loops that can shift on timescales from years to decades. The seafloor forms the lower boundary of the ocean and introduces another set of exchanges. Rivers deliver sediments and dissolved minerals. Coastal erosion adds material. Biological debris sinks and accumulates. In some places, hydrothermal vents occur where seawater penetrates cracks, heats. In contact with hot rock, dissolves minerals and emerges as hot mineral-rich fluid. Hydrothermal vents create chemical gradients that support chemosynthetic microbial communities using chemical energy rather than light. This is a striking example of life supported by interior energy, and it shows how the ocean connects to geology. Hydrothermal circulation also alters ocean chemistry, exchanging elements between seawater and crust. What is known is that vents exist, that they support unique ecosystems, and that they contribute to global geochemical cycles for certain elements. What remains uncertain is the full variability of vent systems through time, and their net influence on long-term ocean composition under different planetary conditions. In this region, the ocean is a layered environment defined by light loss, temperature gradients, pressure increase and circulation. Its surface is an interface with air exchanging gases and heat. Its depths are a high-pressure reservoir with slow movement and specialized life. Currents and mixing connect the layers, redistributing heat and chemicals. Size overwhelms intuition because the ocean is thin compared with the planet, yet contains vast volumes and extreme gradients, and because the deep ocean operates on timescales far longer than weather. This completes the ocean region, preparing for the next inward step where liquid gives way to solid, and the planet's rigid outer shell becomes the focus. Beneath oceans and continents, the next inward region is the planet's rigid outer shell of rock. On Earth, this shell includes the crust and the uppermost mantle, where rock is cool enough to behave mostly as a rigid solid on human timescales. This combined rigid layer is called the lithosphere. It is broken into tectonic plates that move slowly over the softer, hotter layer beneath. The shell is thin compared with the planet's radius, yet it controls the surface landscape and many hazards, and it acts as the main pathway through which internal heat escapes. Size overwhelms intuition here through time and pressure, rather than through distance alone. The plates move only a few centimeters per year, but over millions of years that becomes thousands of kilometers. The crust is the outermost part. Oceanic crust is thinner and denser, made mostly of basaltic rock. Continental crust is thicker and less dense, richer in silica, and capable of persisting for billions of years. Oceanic crust forms at mid-ocean ridges where plates pull apart and hot mantle material rises. As it rises, pressure decreases and part of it melts. The melt solidifies to form new crust. As the crust moves away from the ridge, it cools, becomes denser, and sinks lower, deepening the ocean basin. Eventually it can reach a subduction zone where it bends and sinks back into the mantle beneath another plate. This recycling means most oceanic crust is geologically young compared with continental crust. Continental crust, because of its buoyancy, resists subduction. It can be thickened, deformed, and metamorphosed, but it often remains at the surface accumulating history. Plate boundaries are the main sites of deformation. At divergent boundaries, plates move apart. New crust forms and shallow earthquakes occur as rock fractures. At convergent boundaries, plates move together. If oceanic crust meets continental crust, the denser oceanic plate usually subducts, creating deep trenches, volcanic arcs, and mountain belts. If two continental plates collide, neither subducts easily, and the crust shortens and thickens, forming high mountain ranges and broad plateaus. At transform boundaries, plates slide past each other, producing earthquakes, but typically little volcanism. These boundary types are simplified, and real boundaries can combine behaviors, but the classification helps keep the region clear. Plate motion concentrates stress at edges. Faults are fractures where blocks of rock move. Stress builds from plate motion and is released when a fault slips, producing an earthquake. The energy travels as seismic waves through Earth. Seismology is used to map interior structure, but within this region the immediate fact is that earthquake distributions outline plate boundaries, tracing where the lithosphere is actively breaking and sliding. Earthquake size depends on the area of fault that slips and how much it slips. Large earthquakes involve long fault segments and significant displacement. The shaking that reaches the surface depends on depth and on the properties of the rocks the waves travel through. Volcanism is another expression of plate dynamics and heat escape. At mid-ocean ridges, basaltic magma rises and forms new seafloor. At subduction zones, water and other volatiles released from the sinking slab lower melting temperatures in the overlying mantle, producing magma that can be more varied in composition. This magma rises and can erupt, building volcanoes. Volcanoes release gases such as water vapor, carbon dioxide, and sulfur compounds. These gases can influence climate and atmospheric chemistry, especially when eruptions inject particles into high altitudes where they reflect sunlight. Over long time, volcanic outgassing contributes to atmospheric composition and to cycles of carbon between interior and surface. The crust is also where surface processes interact with deep processes. Erosion breaks down rock. Rivers transport sediment. Sediments accumulate in basins compact into sedimentary rock and can be buried and metamorphosed under heat and pressure. Uplift exposes deeper rocks. This rock cycle connects the surface to the interior, but it operates through many steps over long time. The rock cycle is not a closed loop in a simple sense because materials can be stored for long intervals in one form. Yet the broad idea is stable rocks are transformed by melting, cooling, burial pressure, and weathering. Size overwhelms intuition here because the transformations are slow and because the crust is thin, yet holds enormous variety in composition and structure. Isostasy provides a way to understand why the crust can support mountains and why it adjusts under changing loads. Isostasy is the tendency of the lithosphere to float on the softer mantle beneath, with thicker, less dense crustal regions standing higher and having deeper roots like an iceberg. When a mountain range forms, crust thickens and sinks deeper into the mantle, supporting high elevation. When an ice sheet grows, it presses the crust downward. When the ice melts, the crust rebounds upward over thousands of years. This shows that the rigid shell is rigid only in a short-term sense. Over long times it can bend and adjust. The lithosphere's strength depends on temperature. Cooler rock is stronger and brittle. Hotter rock becomes weaker and can deform ductilely, meaning it flows slowly without fracturing. This is why the base of the lithosphere is defined by a temperature range where rock transitions from mostly rigid to more easily deforming. Water influences this behaviour. Water can weaken rocks by aiding mineral reactions and by reducing friction along faults. In subduction zones, water carried down in minerals and sediments affects melting and volcanism. At the surface, water drives weathering and erosion. The presence of water can therefore make plate tectonics more likely by weakening the lithosphere and enabling subduction, though this is not the only factor. Differences between Earth and Venus may involve water content, surface temperature, and lithospheric strength. What is known is that Earth has active plate tectonics, and that water affects rock strength and melting. What remains uncertain is the full set of conditions needed to initiate and sustain plate tectonics over billions of years on other planets. Even so, the crustal region can be held as the active shell where internal heat meets surface environment. The crust also records magnetic and chemical history. At mid-ocean ridges, new basalt cools and locks in a magnetic signature aligned with Earth's magnetic field at the time. As the field reverses over geological time, stripes of alternating magnetic polarity are created on the seafloor symmetric about ridges. This record helped confirm seafloor spreading and plate tectonics. Chemical signatures including isotopic ratios record mantle sources, crustal recycling, and the history of oceans and atmosphere. Through these records, the thin crust becomes a library of deep and surface interactions. Size overwhelms intuition, because the crust's thickness is small relative to Earth, yet it holds the landscapes and the archive of deep time. The plate motions that reshape it are slow, but their consequences are large when integrated over millions of years. This region is complete when the rigid shell is held as a moving mosaic of plates thin yet powerful, where earthquakes and volcanoes mark boundaries where continents and oceans are built and recycled, and where the planet's internal heat and surface water continually interact. The next inward step will move below the rigid shell to the mantle, where rock is hotter and can flow slowly, driving the plate motions from below. Below the rigid outer shell, the next inward region is the mantle, where rock remains mostly solid, yet flows slowly over long time. The mantle is the largest part of a rocky planet by volume on Earth, extending from beneath the crust down to the core. It is made mainly of silicate minerals rich in oxygen, magnesium, silicon, and iron. The mantle's behavior overwhelms intuition because it asks the mind to accept rock as something that can move like a fluid without being molten. On human timescales, mantle rock is solid and strong. On geological timescales, under high temperature and pressure, it creeps. Creep is slow, continuous deformation under stress. This slow flow transports heat upward and drives the motion of tectonic plates. The mantle is therefore the engine room of the planet's long-term surface change, even though it is hidden. Temperature increases with depth, but pressure also increases, raising melting points. This is why most of the mantle is solid. Partial melting occurs in specific conditions, such as when mantle rises and pressure decreases, or when water lowers melting temperatures, but the bulk remains solid. The mantle's capacity to flow comes from defects in crystal structures, and from the ability of minerals to change shape under stress when heated. Viscosity. The resistance to flow is high in mantle rock compared with liquids, but it is not infinite. Viscosity depends strongly on temperature. Hotter mantle flows more easily. Cooler mantle is stiffer. This creates strong contrasts within the mantle. Cold subducting slabs can be much more viscous than surrounding mantle, while hotter upwelling regions can be less viscous. These contrasts shape convection patterns. Convection is the dominant mode of heat transport in the mantle. Convection occurs when warmer, less dense material rises and cooler, denser material sinks. Heat sources include residual heat from formation, heat released by differentiation, and heat from radioactive decay within the mantle. The surface and crust act as a cooling boundary. When mantle material near the top cools, it becomes denser and can sink, especially when attached to a subducting plate. When mantle material deep down is heated, it becomes less dense and tends to rise. Over time, this sets up circulation. The pattern is not a simple set of neat rolls. It is complex with sinking slabs, rising plumes, broad upwellings, and lateral flow. Yet the basic principle remains stable convection, moves heat and material. Seismic waves provide much of what is known about mantle structure. Earthquakes generate waves that travel through Earth. Their speeds depend on temperature composition and phase. Seismic tomography uses variations in travel time to map regions where waves travel faster or slower. Faster regions often correspond to cooler, stiffer material such as subducted slabs. Slower regions often correspond to hotter or partially molten regions. Tomography reveals that slabs can extend deep into the mantle, sometimes reaching the lower mantle. It also reveals broad, low-velocity regions near the base of the mantle, suggesting hot or compositionally distinct material. The mantle is not uniform. It contains chemical heterogeneity. Some regions may preserve material from early Earth, while others are products of recycling through subduction and melting. Evidence for this comes from the chemistry and isotopic compositions of volcanic rocks, such as those erupted at mid-ocean ridges and hotspots. Isotopes of elements like helium, neodymium, and lead can indicate different mantle source reservoirs. What is known is that mantle sources vary, and that some plume-related lavas show signatures consistent with less processed material. What remains uncertain is the exact distribution and longevity of distinct reservoirs, and how efficiently mantle convection mixes the mantle over time. The mantle also changes with depth through mineral phase transitions. As pressure increases, minerals adopt denser crystal structures. In Earth's mantle, there is a transition zone between the upper and lower mantle, characterized by major phase changes. These changes create seismic discontinuities, observed as reflections and refractions of seismic waves. A well-known boundary occurs near about 410 kilometers depth, where olivine transforms to a denser structure. Another occurs near about 660 kilometers, where further transitions happen. These boundaries can influence convection. They can slow sinking slabs or rising plumes depending on temperature and composition, and they can act as temporary barriers to flow. They also influence density and therefore buoyancy. The transition zone may also store water in minerals that can incorporate hydroxyl groups, meaning water-related components within their structure. This suggests that water can be transported deep into the mantle and stored for long times, affecting melting and rheology, meaning deformation behavior. The exact amount and distribution of such water remain uncertain, but the possibility is supported by experiments and by some seismic observations. The lower mantle has different mineral structures and may be more viscous on average. Convection still occurs, but flow patterns may be broader. Some models suggest whole mantle convection, where material circulates from surface to deep mantle and back. Others emphasize layered convection with partial separation. The evidence suggests that slabs can penetrate deep, supporting significant whole mantle circulation, while some chemical layering may persist. The deepest mantle near the core mantle boundary is especially complex. This boundary is a sharp change from solid silicate mantle to liquid metallic core. Heat flowing out of the core creates a thermal boundary layer in the lowermost mantle. This region can be hotter and may host large-scale structures such as large, low-shear velocity provinces, observed as broad regions where seismic shear waves travel unusually slowly. These regions could be hotter, compositionally different, or both. Their edges may be sites where plumes originate. What is known is that seismic studies reveal large structures in the lowermost mantle, and that the core mantle boundary is a major thermal and chemical interface. What remains uncertain is the detailed composition of these deep structures and their exact role in plume generation. The mantle's surface expression includes hotspots and large volcanic provinces. A hotspot is a region of persistent volcanism, not directly tied to a plate boundary, often explained by a mantle plume. A plume is an upwelling of hot mantle that rises from deep levels and partially melts beneath the lithosphere. As the plate moves, a chain of volcanoes forms with older volcanoes farther from the active hotspot. This pattern is seen in places like Hawaii. Large igneous provinces such as flood basalts may reflect the arrival of a plume head, a larger initial pulse of hot mantle that produces massive eruptions over a relatively short geological time. These eruptions can release gases that affect climate. The mantle also influences long wavelength surface elevation through dynamic topography. Upwelling mantle can push the surface upward, while downwelling mantle can pull it downward. These effects are subtle compared with the mountain building from crustal shortening, but they can influence sea level relative to land and the distribution of sedimentary basins. In this region, size overwhelms intuition because the mantle's motion is slow and hidden, yet it reshapes the entire surface over time. It also involves huge masses moving through solid-state creep, driven by small density differences in heat flow. The motion is not visible directly, but it is inferred from plate motions, seismic images, volcanic patterns, and gravity anomalies. The mantle completes the inward step from rigid plates to the slow convecting interior, setting up the next inward region, where material changes from silicate rock to metallic core, and where motion becomes a generator of magnetism rather than plate movement. Below the mantle, the next inward region is the core, where the planet's center is dominated by metal, and where motion is tied to magnetism. On Earth, the core is mainly iron with some nickel and a smaller fraction of lighter elements. It is divided into a liquid outer core and a solid inner core. This division is set by pressure and temperature. Temperature rises toward the center, but pressure rises even more, and high pressure can keep iron solid at temperatures that would melt it at lower pressure. In the outer core, iron remains liquid. In the inner core, iron crystallizes into a solid sphere. This region overwhelms intuition because it combines extreme conditions with indirect evidence. No direct samples exist. Knowledge comes from how waves and fields behave at the surface, yet the picture is coherent and constrained. The existence of a liquid outer core is revealed by seismic waves. Earthquakes generate compressional waves that can travel through solids and liquids, and shear waves that travel only through solids. Observations show that shear waves do not pass through the outer core, indicating it is liquid. Compressional waves slow down and refract there, producing shadow zones where they are not detected at certain angles. By analyzing these patterns, scientists infer the size and properties of the core. The inner core is inferred from subtle reflections and changes in compressional wave behavior, consistent with the solid region at the center. Earth's overall density and moment of inertia also constrain core mass because a planet with a large dense core has a different rotational response than one with a more uniform interior. Together, these lines of evidence point to a dense metallic center. The core matters because it is a major source of heat for the mantle and because it powers the geodynamo. Heat flows outward from the core into the mantle across the core-mantle boundary. This boundary is both a thermal and chemical interface. The mantle is silicate rock. The core is metallic liquid. Heat crossing this boundary influences mantle convection, and mantle convection influences how efficiently heat is removed from the core. This coupling affects the core's cooling rate, and through cooling the growth of the inner core. As the outer core cools, iron solidifies at the inner core boundary. This releases latent heat, the heat released when a liquid becomes solid. It also releases lighter elements because the solid inner core preferentially incorporates iron and excludes some lighter components. These expelled light elements make the surrounding liquid less dense, creating compositional buoyancy. Both latent heat and compositional buoyancy drive convection in the outer core. This is similar in concept to mantle convection, but the material is different, and the consequences include magnetism. The outer core is an electrically conducting fluid. When it moves, it can generate electric currents. Electric currents generate magnetic fields. Under the right conditions, the generated magnetic field supports the currents in a self-sustaining feedback loop, producing a dynamo. Rotation is crucial because it organizes fluid motion. In a rotating body, the Coriolis effect influences flow tending to align convection into column-like structures parallel to the rotation axis. This organization helps create large-scale coherent magnetic fields rather than purely tangled small-scale fields. The result on Earth is a magnetic field that at the surface is roughly dipolar, meaning it resembles a bar magnet with a north and south pole, though it also has complex variations. The field extends outward, forming the magnetosphere which interacts with the solar wind. Charged particles from the solar wind are deflected around the magnetosphere, though some enter near the poles and create auroras when they collide with atoms in the upper atmosphere. This interaction shows that the core's motion influences the planet's space environment. It is another way size overwhelms intuition. A deep interior flow generates a field that reaches far beyond the atmosphere. Earth's magnetic field changes with time. The positions of the magnetic poles drift. The field's strength varies. Over geological time, the field reverses polarity so magnetic north and south swap. Reversals are recorded in rocks, especially basalt formed at mid-ocean ridges. When basalt cools, magnetic minerals align with the prevailing field direction and lock in that direction. The seafloor, therefore, preserves stripes of magnetic polarity that reflect the history of reversals and seafloor spreading. The reversal record is irregular. The time between reversals can vary widely. What is known is that reversals are part of the dynamo's behavior and that they have occurred many times. What remains uncertain is the precise internal fluid evolution that triggers a reversal and why reversal frequency changes. Numerical simulations of dynamos can produce reversals under certain conditions, suggesting that reversals are emergent properties of the system rather than the result of a single external cause. The core's composition includes lighter elements beyond iron and nickel. The density of the core inferred from seismic data is lower than that of pure iron at core conditions, implying the presence of lighter components such as sulfur, oxygen, silicon, carbon, hydrogen, or a combination. Laboratory experiments and theoretical calculations at high pressure and temperature help constrain possible mixtures, and models of Earth's formation provide additional constraints. What is known is that some lighter elements are present. What remains uncertain is the exact combination and proportions. This uncertainty affects details of core conductivity, melting temperature, and convection patterns, but it does not change the main structure, a liquid outer core and solid inner core. The core also affects Earth's rotation through coupling with the mantle. Variations in core flow and electromagnetic interactions can exchange angular momentum between core and mantle, contributing to small variations in the length of day. These changes are tiny but measurable. The inner core may rotate slightly differently from the mantle inferred from subtle, seismic observations, but the magnitude and variability remain debated. The important stable point is that the core is not static. It is a moving system. The inner core grows slowly as the planet cools. The outer core circulates, and that circulation maintains the magnetic field. The timescale of core evolution is long. The inner core likely formed after Earth's early history, but estimates of its age vary, reflecting uncertainties in core thermal conductivity and in the planet's cooling history. What is known is that Earth has sustained a magnetic field for much of its history, as indicated by paleomagnetic signatures in ancient rocks. This implies that energy sources for the dynamo have persisted over billions of years. The specific balance between cooling latent heat and compositional buoyancy may have changed over time as the inner core grew, but the dynamo has remained active. Comparing Earth to other planets clarifies the role of the core. Mars likely had an early dynamo and lost it, suggesting its core cooled, or changed, in a way that reduced convection. Mercury has a weak magnetic field indicating a small but active dynamo. Venus lacks a strong global field today, possibly because of slow rotation or different core mantle heat flow. The giant planets have different dynamos with conducting fluids such as metallic hydrogen in Jupiter and Saturn, and ionic water-ammonia mixtures in Uranus and Neptune. These examples show that magnetic fields depend on internal structure, energy flow and rotation, not simply on size. In this region, size overwhelms intuition, because the core's conditions are extreme and hidden, yet its field is measurable, and its influence extends outward. The core is a boundary of material change from silicates to metal, and a boundary of process change from mantle creep to liquid convection that generates magnetism. Completing this region means holding the core as a layered metallic center, a liquid outer core convecting under heat and composition differences, a solid inner core crystallizing and growing, and a magnetic field arising from organized fluid motion. The next inward step will shift scale again away from planetary interiors and toward the smaller scales of living systems where size overwhelms intuition through complexity and number rather than distance and pressure. After the planet's deep interior, the inward path shifts to the scale of living systems where size overwhelms intuition through the density of activity and the number of interacting parts. The basic unit here is the cell. A cell is a bounded system that maintains an internal environment, carries genetic information, and uses energy to sustain organized chemistry. Cells vary widely in size and complexity, but they share core physical features: a membrane boundary, a watery interior with dissolved ions and molecules and networks of chemical reactions that transform energy and matter. This cell is small compared with any geological layer, yet within it gradients flows, and molecular machines operate continuously. In this region, the aim is to hold the cell as a physical object governed by diffusion chemistry and energy conversion, not as an abstract symbol of life. The boundary of a cell is the cell membrane. The membrane is mainly a lipid bilayer. Lipids have water-loving heads and water-avoiding tails. In water, they arrange into a double layer with tails inward and heads outward, creating a flexible sheet. This sheet forms spontaneously because it reduces unfavorable interactions between water and the lipid tails. The membrane is not a static wall. It is fluid with lipids and proteins moving within it. Embedded proteins act as channels, pumps, receptors, and anchors. The membrane's key function is selective permeability. Some small molecules can diffuse through. Many important substances cannot cross freely and require transport proteins. This selectivity allows the cell to maintain differences between inside and outside, such as ion concentrations and pH. pH measures acidity, and is linked to the concentration of hydrogen ions. Many cellular processes require a narrow pH range, so cells regulate it actively. The cell interior, the cytoplasm, is water, with salts, proteins, nucleic acids, sugars, and many other molecules. It is crowded. Crowding matters because it alters how molecules move and meet. Diffusion still occurs, but pathways are constrained and large molecules can move more slowly. Diffusion is the random spreading of molecules due to thermal motion. In a small cell, diffusion can be effective over short distances, but as distances increase, diffusion becomes slower. This is one reason many cells remain small, and why larger cells use internal transport systems. Cells also use compartmentalization, separating reactions into regions with distinct chemistry. In eukaryotic cells, compartments are often membrane-bound organelles. In bacteria and archaea, compartmentalization can still exist through localized regions and protein-based microcompartments. Eukaryotic cells typically have a nucleus where DNA is stored. DNA, deoxyribonucleic acid, is a long polymer made of nucleotides. The sequence of nucleotides encodes information for building proteins. Proteins are polymers of amino acids folded into specific shapes. Many proteins are enzymes that speed up chemical reactions. Enzymes work by lowering activation energy, the energy barrier that must be crossed for reactants to become products. Without enzymes, many reactions needed for life would occur too slowly under typical biological conditions. DNA information is used through gene expression. Gene expression involves transcription, where DNA is copied into ribonucleic acid, and translation, where ribosomes read ribonucleic acid to assemble amino acids into proteins. Regulation of gene expression allows cells to respond to changes by producing different proteins as needed. Energy is central. Cells must continually use energy to maintain order and drive reactions that would not happen spontaneously. A key energy carrier is adenosine triphosphate, commonly called ATP. ATP stores energy in its phosphate bonds. When ATP is converted to adenosine diphosphate, and a phosphate group energy is released. Cells use this energy to power pumps build molecules and move structures. ATP is produced through pathways that capture energy from food molecules or from light. In many eukaryotic cells, mitochondria produce most ATP through oxidative phosphorylation. This process uses an electron transport chain in the inner mitochondrial membrane. As electrons move through the chain, protons are pumped across the membrane, creating a proton gradient. A gradient is a difference across space here, a difference in proton concentration. The gradient stores energy. Protons flow back through an enzyme called ATP synthase, driving ATP production. This mechanism is a form of chemiosmosis, meaning energy conversion driven by an ion gradient across a membrane. Similar systems exist in bacteria in their cell membranes and in chloroplasts of photosynthetic organisms, where light energy drives electron flow and proton pumping. The cell therefore uses membranes not only as boundaries but as energy devices. Ion gradients are also fundamental. Cells often maintain higher potassium inside and higher sodium outside. They also regulate calcium, tightly keeping free calcium low in the cytoplasm. These gradients create electrical potentials across the membrane. An electrical potential is a difference in charge distribution that can influence the movement of ions and charged molecules. The combination of concentration gradient and electrical potential is called an electrochemical gradient. Electrochemical gradients enable rapid signaling in nerve cells and muscle contraction, but even in non-excitable cells they drive transport and maintain internal conditions. Maintaining gradients requires energy, because pumps must move ions against their natural diffusion direction. The cell uses energy to create gradients and then uses gradients to do work. This is another way size overwhelms intuition across distances that tiny differences can be made large, and those differences can be harnessed. Cells also have internal scaffolding and transport. The cytoskeleton is a network of protein filaments that provides structure, organized as internal components, and enables movement. In eukaryotes, microtubules and actin filaments are major components. Motor proteins move along these filaments carrying vesicles. Vesicles are small, membrane-bound sacs used to transport materials. Cells use vesicles to move proteins and lipids to take in material from outside and to release substances. This directed transport complements diffusion and allows organization on larger cellular scales. Cells sense their environment through receptors. Receptors bind specific molecules and trigger internal signaling pathways. Signals can involve changes in protein activity, shifts in ion concentrations, or alterations in gene expression. Signaling pathways often involve cascades, where one activated protein activates another, amplifying the signal. This allows small external changes to produce meaningful internal responses. Yet signaling also requires control to prevent runaway activation. Cells use feedback mechanisms to stabilize responses. In bacterial cells, signaling can be simpler but still effective, using receptor proteins and regulatory networks to adjust metabolism and movement. The cell's chemical network includes synthesis and breakdown. It builds membranes, proteins, nucleic acids, and complex carbohydrates. It also breaks down molecules to release energy and recycle components. The balance of building and breaking is metabolism. Metabolism is organized into pathway sequences of enzyme-catalyzed reactions, where the product of one step becomes the input of the next. These pathways allow control. By regulating one enzyme, a cell can slow or speed the entire pathway. This coordination allows the cell to adapt to resource availability and stress. The cell also copes with damage. Reactive molecules can alter proteins and DNA. Cells have repair systems to correct DNA errors and to refold or degrade damaged proteins. These systems are needed because the cell's environment is warm and reactive, and because thermal motion and chemistry inevitably produce occasional errors. Stability is achieved through continual maintenance. In this region, what is known is that all known life uses cell-like systems, with membranes, genetic information, and metabolism. The broad mechanisms of energy conversion, gene expression, and membrane transport are shared across life, suggesting deep common ancestry. What remains uncertain in detail is the full range of possible cellular architectures in other environments and the precise pathways by which the earliest cells emerged on Earth. Yet the physical requirements are clear: a boundary to maintain gradients, chemistry to build and repair, and energy flow to sustain organization. The cell therefore stands as a small system, where size overwhelms intuition by packing continuous activity into a microscopic volume. Within it, molecules move by diffusion reactions, proceed through enzymes, gradients store energy, and information is stored and used. This completes the cell region, setting up the final inward step, where the behavior of molecules and atoms under thermal motion and quantum rules becomes the foundation beneath all biological structure. At the final inward step, the cell's organized activity resolves into the behavior of molecules and atoms. Here size overwhelms intuition, not because distances are large, but because the smallest motions are constant, and because the rules of matter at this scale differ from everyday expectations. A molecule is a group of atoms held by chemical bonds. An atom is the smallest unit of an element that retains the element's identity. In living systems and in planetary materials, molecules and atoms are always in motion. Thermal motion is the continual jostling and vibration of particles due to temperature. Temperature is a description of the average kinetic energy of this motion. In a warm environment like a cell, molecules collide constantly, change orientation, and explore many configurations. The stability seen at larger scales arises from statistical regularities and from energy-driven constraints, not from stillness. Water is the most important molecular context for life on Earth. Water's influence comes from its polarity. Water molecules have uneven charge distribution, allowing them to form hydrogen bonds. Hydrogen bonds are weak attractions involving hydrogen and electronegative atoms, and they form and break rapidly in liquid water. This creates a dynamic network that gives water its high heat capacity and strong solvent properties. Water surrounds ions and polar molecules, forming hydration shells that stabilize them in solution. This allows many biochemical reactions to occur in a fluid medium. Water also influences how nonpolar molecules behave. Nonpolar groups tend to cluster in water because it allows water's hydrogen bond network to remain more intact. This is the hydrophobic effect. It drives the formation of lipid membranes and helps proteins fold by tucking nonpolar parts inward. These are examples of how large biological structures emerge from simple molecular interactions. Diffusion is a central consequence of thermal motion. Molecules spread from regions of high concentration to regions of low concentration because random motion leads to net movement down a gradient. In a cell, diffusion moves small molecules and gases quickly over short distances. In crowded cytoplasm, diffusion can be slowed, and cells use directed transport, but diffusion remains the default. Reaction rates depend on collisions. For a reaction to occur, molecules must collide with sufficient energy and in the right orientation to cross an activation barrier. The activation barrier is an energy threshold between reactants and products. Most reactions in water at moderate temperatures proceed slowly without help, because only a small fraction of collisions meet the needed conditions. Enzymes accelerate reactions by lowering the activation barrier and by positioning molecules in favorable orientations. Enzyme function depends on precise shapes and charge distributions, which arise from chemical bonding and from the arrangement of electrons in atoms. At the atomic scale, electrons do not orbit like small planets. They occupy probabilistic regions called orbitals. Orbitals have allowed energy levels. The structure of these levels explains why atoms form bonds and why elements have characteristic chemical behavior. The periodic table organizes elements by electron configuration. Elements in similar groups have similar outer electron patterns and therefore similar chemistry. This regularity is a foundation for material properties in rocks, in oceans, and in cells. Chemical bonds are expressions of electron behavior. In covalent bonding, atoms share electrons. In ionic bonding, electrons are transferred and oppositely charged ions attract. In metallic bonding, electrons are shared across many atoms, allowing conductivity and malleability. These bonding types determine why salt crystals are brittle, why metals conduct electricity, and why silicate minerals form strong frameworks. In biological molecules, covalent bonds create stable backbones, while weaker interactions such as hydrogen bonds, ionic attractions, and van der Waals forces shape folding and binding. Van der Waals forces are weak attractions arising from temporary charge fluctuations. Individually small, they can be significant in large numbers, contributing to how molecules pack together. The cell structure is therefore a balance of strong bonds that build molecules and weaker forces that allow flexibility and reversible interactions. Energy at this scale moves in small steps. Chemical energy is stored in bonds and released when bonds are rearranged. In respiration, electrons are transferred through a chain of carriers, releasing energy gradually, which is captured by pumping ions and forming ATP. In photosynthesis, photons excite electrons, enabling reactions that store energy in chemical form. The efficiency of these systems depends on controlling electron flow and minimizing waste, but some energy always becomes heat. Heat is the natural dispersion of energy into random motion. The cell cannot avoid it. Instead, it manages it through steady exchange with the environment and through the fact that reactions occur in aqueous solution, which can absorb and distribute heat. At the atomic level, light interacts with electrons through quantized transitions. Electrons can move between energy levels by absorbing or emitting photons with specific energies. This creates spectral lines, which are signatures used to identify elements and molecules. The same principle used to read the composition of distant stars is used in laboratories to study biomolecules and atmospheric gases. The consistency of atomic transitions across space and time is one reason science can connect cosmic observations to local chemistry. Yet quantum behavior also imposes uncertainty in a specific sense. The exact position and momentum of an electron cannot both be known with perfect precision. This is a fundamental feature described by the uncertainty principle. It does not make chemistry unpredictable in practice, because the probabilities are stable, and because large numbers of interactions average into reliable outcomes. But it does mean that at the smallest scale, nature is described statistically. In a cell, this statistical foundation becomes practical stability, because countless molecular events occur each moment producing consistent average behavior. Another source of size-overwhelming intuition here is the number of molecules. A single cell contains an enormous number of water molecules, ions, and proteins all moving and interacting. Even a small volume of liquid contains far more molecules than can be imagined individually. This is why chemistry uses concentration, temperature, and pressure as useful macroscopic variables. These variables summarize the collective behavior of vast numbers of particles. The cell is stable because it regulates these variables locally. It maintains ion concentrations, pH, and metabolite levels within ranges where reactions and structures remain functional. When conditions drift, proteins can unfold, membranes can change fluidity, and reactions can slow or accelerate. Life's maintenance is therefore a continual act of keeping molecular statistics within workable bounds. The same molecular principles also underlie planetary materials. In the mantle, minerals transform under pressure because atomic lattices reorganize. In the core, ions phase changes depend on atomic arrangements under extreme pressure. In atmospheres, gas behavior arises from molecular collisions and energy distributions. In oceans, solubility and acidity arise from molecular interactions and equilibria. The inward journey to molecules and atoms is therefore not a detour from earlier scales. It is the foundation that makes earlier scales coherent. Gravity shapes the larger structures, but the behavior of matter within those structures depends on atomic bonding phase changes and radiative interactions. Light carries information across space because atomic transitions produce and absorb specific wavelengths. The universe's vast scale is readable because atoms behave consistently. At this final region, the focus settles on the smallest moving parts described here: atoms with nuclei and electron clouds, molecules held by bonds all in thermal motion. Order at larger scales arises from constraints, gradients, and steady energy flow, not from immobility. The overwhelming part of intuition is that a seemingly solid, stable world is made of ceaseless motion and probabilities, yet those probabilities produce dependable regularity when counted in large numbers. This completes the inward path from the largest measurable frame to the smallest physical units used here. The pace softens further now. The details can remain present without effort. Molecules continue to drift and turn in water. Bonds hold vibrations, pulse, and collisions come and go without needing attention. The larger structures that seemed so vast can be allowed to fade into the background as if they have been placed gently on a shelf. The cosmic web, the galaxies and the stars remain, but they no longer press for comparison. A single world remains, then its air, then its water, then the rock beneath, and then even those layers dissolve into the quiet idea of matter, arranged and rearranged. Nothing here asks for a conclusion. The physical rules continue without comment. Energy flows gradients rise and relax, and the smallest motions stay constant. The mind can let the scale feel distant, not as a problem to solve, but as a steady fact that does not require holding. The narration becomes still, leaving only the final line in a calm and neutral way.